Hey, what's up everyone? Welcome to Stoichiometry/Solutions Part 2. Today we're going to be talking about a limiting reactant. So what is a limiting reactant? The limiting reactant is the reactant that runs out first during a chemical reaction. And a really common analogy that people use to kind of understand what a limiting reactant is a bike. So for a bike, you're going to need a lot of things, but you're going to need a frame and two wheels. So one frame plus two wheels is going to result in one bike. Now, in this case, the frames and the wheels are the reactants and the bike is the product. Now, if I give you something like 10 frames, you could hypothetically make 10 bikes. But what if instead of 20 wheels, I give you two wheels? Well, then you can only make one bike. So it doesn't matter that you have 10 frames because you can only use not one of them. So in this situation, it doesn't matter if you have 10 frames, 100 frames, 1,000 frames, you can only make one bike because you're limited by how many wheels you have. So in this scenario, the wheels is the limiting reactant. Now let me flip the situation. Let's say instead of two wheels, I give you 100 wheels. With 100 wheels, you could hypothetically make 50 bikes. But instead of giving you 50 frames, let's say I give you only 3 frames. That means you can only make 3 bikes. It doesn't matter how many wheels you have left over because your limiting reactant in this case is frames. I could give you 1,000 wheels, I can give you 10,000 wheels. You still can't make any more bikes because you're limited by how many frames you have. So in this situation here, the frames is the limiting reactant, but in the other situation, we saw that wheels was the limiting reactant. So while in this analogy, we use something like frames and wheels making a bike, this works the exact same way for chemical reactions. Let's talk about ways to find limiting reactant in a chemical equation. There's going to be 2 methods. The first method is going to be comparing the moles of reactants. So with this method, the first step is to calculate the number of moles of each reactant, and the second step is to determine how many moles of one reactant you need to fully react with all the moles of the other reactants. Now, this doesn't really make sense until you do like a problem. So let's look at this problem. We have ammonia reacting with copper oxide to produce nitrogen gas, copper solid, and water. We're told that 18.1 grams of NH3 is reacted with 90.4 grams of copper oxide, and we're asked to determine the limiting reactant. Now, before you can even start the steps, it's important that you have a chemical equation down. And for this problem, although we're given a chemical equation, you'll notice that it's not currently balanced. So to balance it, we'll need to add a 2 in front of the ammonia. We will need a 3 in front of the copper, and that's going to produce N2 plus 3 copper plus 3 waters. And that should be balanced. Okay, so now we're ready to start the steps. So first of all, we need to calculate the number of moles of each reactant. So first, we're given 18.1 grams of NH3. To turn that into moles, we divide by the molar mass, and the molar mass of ammonia is 17 grams. So 17 grams of ammonia is 1 mole of ammonia. So we have 1.06 moles of ammonia. And let's do the same for the copper oxide. So we're told that we have 90.4 grams of copper oxide. And the molar mass of copper oxide is about 79.5 grams of copper oxide per 1 mole of copper oxide. And that's about 1.14 moles of copper oxide. Okay, so that's the first step. Let's look at step 2. So determine how many moles of one reactant you need to fully react with all the moles of the other reactants. So how many moles of copper oxide are we going to need to react in order to fully react 1.06 moles of ammonia? Well, if you notice, ammonia and copper oxide are in a 2:3 ratio. So in order to find how many moles of copper oxide we're going to need, we need to multiply this value by 3/2. And that's going to get us that we need about 1.60 moles of copper oxide to fully react all 1.06 moles of ammonia. And now let's do the same for the copper oxide. So we need to multiply this by 2 over 3 because again, ammonia and copper oxide are in a 2 to 3 ratio. So we're going to need 0.76 moles of ammonia to fully react 1.14 moles of copper oxide. Now you'll notice here that we have 0.76 or more moles of ammonia, but we don't have 1.60 moles of copper oxide. And what this is telling us is that the copper oxide is the limiting reactant. We have more ammonia than we really need, but we're limited by how much copper oxide we have. So in this case, since we need more copper oxide than we have, copper oxide is our limiting reactant. I said there were two methods, so let's look at the second method, and it's going to involve comparing the amounts of products that can be produced. The first step is going to be the same, so we need to calculate the number of moles of each reactant, but the second step is to determine how many moles of product you can make with the moles of each reactant that you have. So let's do the same problem again, but with this method. We're going to need to balance it out again, so let's balance it. It's 2NH3 plus 3 copper oxide produces nitrogen gas plus 3 copper solid and 3 water gas. Let's quickly do the first step again. So 18.1 grams of NH3 and the molar mass of ammonia is 16 grams per 1 mole of ammonia. So we have 1.06 moles of ammonia. Let's do the same for copper oxide. So 90.4 grams of copper oxide times the molar mass, which is 79.5 per 1 mole of copper oxide. So we have 1.14 moles of copper oxide. Okay, so that's the first step. Let's look at the second step. So determine how many moles of product you can make with the moles of each reactant that you have. So for this, we're going to need to select one of the products. It doesn't matter which one you select. You just need to select one and use that for both of them. So let's use the nitrogen in this example because it has a coefficient of 1. That should make things, I don't know, maybe a bit easier. So how many moles of nitrogen gas are we going to produce with 1.06 moles of ammonia? Well, since nitrogen gas and ammonia are in a 1 to 2 ratio, if we multiply this number by 1/2, we should get how much nitrogen gas will be produced. So this will come out to 0.53 moles of nitrogen gas. And for the other value, for the copper oxide, we need to multiply this value by 1/3. And that's because nitrogen and copper oxide are in a 1 to 3 ratio. So with 1.14 moles of copper oxide, you can make 0.38 moles of nitrogen gas. And so what you notice here is that the copper is producing less nitrogen gas than the ammonia. And that's telling you that copper oxide is the limiting reactant. So with both methods, we got the same answer. And that shows you it doesn't matter which method you pick, you're going to get the right answer. It's kind of just preference. Okay, let's do one more problem from an actual test. This is the 2014 local exam problem 2. So in the diagram above, the paired open spheres represent H2 molecules and the paired solid spheres represent N2 molecules. When the molecules in the box react to form the maximum possible amount of ammonia molecules, what is the limiting reactant and how many molecules of NH3 can be formed? So we know that we're reacting nitrogen gas with hydrogen gas to produce ammonia. And as always, it's helpful to write the equation that's happening here, the reaction that's happening here. And of course, we're going to need to balance this too. So we're going to need a 2 here and a 3 here, and that looks balanced. Now let's look at the diagram to see how many N2 molecules we have and how many H2 molecules we have. So the open spheres represent H2 molecules, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H2 molecules, and the solid spheres represent the N2 molecules, so 1, 2, 3, 4, 5 N2 molecules. And we're going to need to find out what the limiting reactant is. And technically we could use either of the two methods, but since the question asks us to find molecules of NH3 that can be formed, it's smarter to use the second method because that will give you the information right away. So how many molecules of NH3 can we produce with 12 molecules of H2? So we have 12 H2 molecules, and since NH3 and hydrogen are in a 2:3 ratio, we need to multiply this number by 2/3, and that gets us that we can produce 8 molecules of NH3. NH3, I'm going to write molecules instead of moles. And I'm going to do the same thing for the nitrogen. So we have 5 nitrogen molecules, and we multiply this value by 2, since ammonia and nitrogen are in a 2:1 ratio, and that guesses that we can form 10 molecules of NH3. Since we can produce less molecules with the hydrogen, then that means hydrogen is our limiting reactant. So H2 is our limiting reactant. React, and we can produce 8 molecules of NH3 with it, and that's our answer. One last note about limiting reactant is that you might see it referred to as the limiting reagent. They're the same thing. The names are interchangeable, so don't let that mix you up. All right, that's all I have. I hope you're able to learn something, and I hope to see you later. Thank you.